Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over Green's theorem. So first off, what is Green's theorem? Well, what Green's theorem is essentially establishes a connection between line integrals and double integrals. And I'll go over how that happens and why it's useful later on, I guess. But firstly, I just kind of want to note that there are some good conditions that need to be met as usual before we use this theorem. So firstly, C must be closed and simple. So what that means is that it has to start and end at the same point for the closed aspect, and then for the simple aspect, it has to be non-self-intersecting, meaning that it won't be taking loops around itself and in itself. And then secondly, the orientation of C matters, and I'll get more into that in just a little bit, but I guess the easiest way to kind of explain the other conditions is let's just go ahead and state what Green's theorem actually is. So Green's theorem states, let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region it encloses. If P of xy and Q of xy have continuous partial derivatives on an open region containing D, then the following is true. So first off, I just kind of want to address a couple of the notational, or not the notational, but the words that are used in here, because, it might be a little bit difficult to digest. Let C be positively oriented. Basically what that means is we're traveling around the curve so that the enclosed region stays on whatever orientation we want, right? So I guess conventionally that is going to be counterclockwise. In calculus, usually positive is going to be counterclockwise. Therefore, let C be a positively oriented means the orientation must be clockwise. As for the piecewise smooth, that essentially just means that the curve can have corners, but it won't have any jumps in it, right? So there won't be any tears in it. So it's going to be continuous. As for the simple closed curve, I kind of spoke about that a little bit. Closed means, like I said, it starts and ends at the same point, and simple means it does not intersect itself, so it doesn't cross itself. Let's go ahead and talk about this P of xy. Essentially what that is, it's just the horizontal component of whatever vector field we're given here. We know that this is a vector field in our vector line integral formula right there, so that P of xy just kind of correlates to the horizontal or x component of that vector field. And similarly, this Q of xy is going to represent the y component, or the vertical component of the vector field in our vector line integral formula. And lastly, just kind of want to talk about this continuous partial derivatives. Essentially what that means is like kind of similar to it being piecewise smooth, there's not going to be any sudden jumps or breaks in the slopes, right? Meaning it is continuous. It's a continuous derivative, something that we spoke about in Calculus 1. So let's just go ahead and kind of break this down a little bit. We kind of have this line integral, and now there's a little circle in the middle of our integral for our vector line integral formula. And essentially what that is, it means that circle, means that the integral is taken over a closed loop. That's essentially what that simple closed curve, that's what it kind of correlates to. So that's definitely one of the bigger kind of conditions that are within Green's theorem, is that it's a simple closed curve, and that can be indicated in the line integral with that little circle in the integral. And as for the right side over here, well, what we're doing here is we're taking the double integral over some region D of the curl of our vector field integrating with respect to area, meaning we're going to be integrating with respect to most commonly dx dy, but we may very well convert to polar as well. But in general, I guess the best way to explain that kind of right side is with a photo here. So let's just go ahead and show a picture. So this picture here it's just kind of like a ellipse of some sort, right? And we essentially, if we recall what curl is it's essentially rotation or the circulation of some point, right? And the curl around this is going to be equal all the way around. So we're going to have all these kind of little whirlpools of some sort. So for this metaphor, I'm just going to go ahead and use whirlpools as a little metaphor here. So these pink kind of swirls, that represents the curl. That's going to be our whirlpools. And when we have so many around, well, they're going to cluster up and make bigger whirlpools, right? So that's kind of what these two depict here. And eventually they're going to keep spinning up, and they're going to get larger and larger and larger until eventually there's just one large whirlpool that's essentially summing up all the tiny rotations, so all of the little curls throughout the interior right here with the little pink swirls. And they're going to cancel and really become just one large curl everywhere except the edge. So this boundary right here is what we're going to be left with. So that's kind of what our integrand is representing there, and that, like I said, we're going to be taking the double integrals. So this is going to be with respect to area over here. So let's just go ahead and talk about y. Well, first off, y area is definitely going to be a pretty large application here. We can find the area of some kind of enclosed region D over here by using only this integral right here. So we could really take a line integral and then find the area of some region D. So it's kind of, you can use it either way, right? So we can try to find the area using this, or we can use this. And then I guess the largest reason that we want to do this, kind of the largest reason that we want to do really anything in calculus, is we're going to be wanting to simplify line integrals. We know already that line integrals can get pretty long and perhaps not always too difficult, but if we can go ahead and save some time by doing a double integral that we're already familiar with and computing the curl, which is pretty simple enough as it is, then we're going to replace a hard curve integral or a hard line integral with an easier double integral. And this can also be applied vice versa. So if we were, like I was trying to explain earlier, if we were given some kind of double integral and it was the curl of some vector field, then we would actually be able to reverse Green's theorem and use the line integral side. And I guess another reason that might as well just mention now for our next video is that Green's theorem kind of sets the foundation for different theorems that we'll be talking about in later, but it sets the foundation for Stokes' theorem as well as something called the divergence theorem. So that is Green's theorem, and I guess we might as well just go ahead and get into an example. So getting into our motivating example here, evaluate the line integral of x minus y dx plus x dy, where c is the parameterized curve, cosine t sine t, t goes from 0 to 2 pi, and we're asked to evaluate it using line integrals and Green's theorem. First off, I just went ahead and drew our parameterization right there. It's going to be a circle with radius 1. We can kind of tell that with cosine, sine, and our radius, r cosine theta and r sine theta, but that r isn't there. There's no coefficient in front of our cosine and our sine, therefore we know that the radius is going to be 1. And the reason that I kind of drew this is because I was talking about earlier, like the orientation matters of our parameterized curve. So our r of t orientation matters, right? Why it matters is because it needs to be positively oriented, so to speak, and that is going to be conventionally counterclockwise. So what are we going to do to make sure that it's positively oriented? Well, we're pretty much just going to be going around our circle and saying, well, where is it pointing? What's the t at that time, right? So what is the parameterization here? Well, we're starting at 0 and ending up at 2 pi, so it would appear that if we plug in, our individual points there, well, if we plug in, the nearest point here, it's going to go from 0 to pi over 2 to pi, so it's really going to go this way. So once again, we're going to go from 0 to pi over 2, 2 pi, to 3 pi over 2, and then to 2 pi. So that is counterclockwise, therefore we know that it is positively oriented. So we can go ahead and advance with Green's theorem, but first of all, we're just going to go ahead and do our line integral part. We're asked to evaluate using line integrals and Green's theorem. So we're just going to go ahead and evaluate it using line integrals first. So let's just go ahead and write down our acronym, PITY. Following this, well, our first step is going to be to parameterize. We should be pretty familiar with line integrals by now. Parameterize. Kindly enough, it was actually already parameterized for us. Our phi is already parameterized, so all I have to do is copy it down. Cosine t, sine t, and our t goes from 0 to 2 pi. Sweet. Go ahead and get into our second step. What would that be? Second step in our PITY, that's going to be integrand. Our integrand, well, we're kind of given this here. Forgot my C. We're given this integral here, so it's could be kind of difficult to decipher. Well, what is our integrand? What is our vector field? We know that this is going to be a vector line integral. Therefore, well, what's our vector field going to be? Our vector field is going to be, just kind of recall earlier with Green's theorem, well, we have a p of xy and a q of xy, and this looks awfully similar to what we have right here. So our p of xy is, I said prior, that's going to correlate to our horizontal term, or typically our x term for our vector field, and our q is going to represent our y term, right? So pretty much what this means is we have our two individual components, they're just already separated, right? So this is going to be our P in this situation, and this is going to be our Q. And just recall that our vector field is going to be the conjunction of these two, right? So our vector field is actually going to be these individual components combined. So it's going to be x minus y will be our x term of our vector field. And our x dy is going to, or our x, I guess, is going to be our y component of our vector field. So that is our vector field right there. So that is our f. And our f of r of t, we're going to be converting to our parameterized curve. We know that our x is cosine t and our y is sine t. So let's just go ahead and plug those in directly. We now have cosine t minus sine t in our x component and cosine t in our y component. Looks good. Go ahead and do our third step, our final step for setting it up. Oh man, I already wrote it down. Oops. Let me see. Well, if I didn't know, well, what is our third step? D in our PITY, our third step, that's going to be differential. And recall that our differential for a vector field, we might just need to kind of remember this, or it could be beneficial to make a formula sheet for yourself. The differential for a vector field line integral formula is just going to be the derivative with respect to t of our parameterization. So it's just going to be our prime of t. And recall that that is just going to be the derivative of our parameterized curve, which is cosine t sine t, with respect to t. A common mistake that one may make is accidentally taking the derivative of our integrand. So we converted our integrand there, and that's a common mistake that some might make, is actually taking the derivative of this, and that's just, you got to make sure that, I would definitely just make sure and check that you're taking the derivative of our parameterized curve. Anyway, so the derivative of cosine t with respect to t, well, we know that's just going to be negative sine t. And the derivative of sine t with respect to t is just going to be cosine t. So that is our differential there. So it looks like we can actually just go ahead and set up our integral, and hopefully it'll be easy enough to evaluate. Hopefully I save myself enough room. Worst case, I'll move my Green's theorem. Integral. Last step of our pity. Integral. Now we're all done with that. So kind of setting up our integral now. Well, let's just reiterate that we're going to have this x minus y dx. Let's see, and then it was plus x dy. That is actually going to be equal to the line integral from 0 to 2 pi of our integrand, which is cosine t minus sine t, cosine t, dotted with our differential, which is negative sine t, cosine t. And this is taken with respect to t. Should be a pretty simple integral that we have here. Let's just go ahead and take the dot product. Well, we have cosine t minus sine t multiplied by negative sine of t. Therefore, let's just go ahead and distribute that negative sine of t out. So we're going to have negative sine t cosine t. And then that is going to be plus sine t squared, sine squared of t. So it looks like our x components are finished. Finishing off our dot product, looks like we're going to have cosine of t and multiplied by cosine of t. So we can just go ahead and add plus cosine squared of t dt. And our favorite trig identity, sine squared of something plus cosine squared of the same thing, that's going to go ahead and equal 1. So that's just going to be 1. So we're going to have from 0 to 2 pi of negative sine t cosine t plus 1 dt. And just kind of finishing our integral off here, we might as well just split this into two different integrals. We'll go from 0 to 2 pi of negative sine t cosine t plus the integral from 0 to 2 pi of 1 dt. Forgot my differential there. Okay. Let's just go ahead and do some u sub here. Well, if we let u equal cosine, I'll write this small. We'll let u equal cosine of t, then du is going to equal negative sine of t dt. Therefore, we kind of just have this integral here of u du from 0 to 2 pi, so that's going to be 1/2 u squared from 0 to 2 pi. Let's go ahead and convert our bounds, actually. Well, what's the cosine of 2 pi? Well, that's going to be 1. And the cosine of 0 is going to be 1 as well. Well, if we're doing 1/2 1 minus 1/2 1, it's going to be 1/2 minus 1/2. Therefore, this is going to turn out to be 0. And then just kind of moving on over here, we're going to have the integral from 0 to 2 pi of 1 dt. Pretty simple integral there. We're going to have t evaluated from 0 to 2 pi, and that's just going to be 2 pi. It's kind of our final answer there for our line integrals. So this is going to equal, what color did I use? What color coordinated? I used yellow for our line integral, and I dipped into our green theorem space. Oops. 2 pi. That's okay. Green's theorem shouldn't take up too much space here. Okay, so evaluating that with our line integral, we see it obviously works, but let's see, maybe Green's theorem would have been an easier way to go about this, and spoiler alert, it is going to be the easier way to go about this. Just kind of a little note that I want to make. First off, once again, I just want to reiterate that I parameterized it and made sure that the orientation is positively oriented, meaning it is counterclockwise. So our curve that we're kind of parameterizing, that was parameterized, that is counterclockwise, therefore is positively oriented. So that's a pretty big step there. It's a circle, so it's closed. It starts and ends at x is equal to 1. So that is also important there. And I guess another kind of hint that Green's theorem may be the best way to use this is the way that we were given this kind of line integral here. We were given to it in that p dx plus q dy form. That should be a pretty good giveaway that, this is going to be a Green's theorem problem that may be easiest. So if we were given this on homework or an exam, then I would definitely argue that seeing that kind of notation and it given that line integral given to us that way, it's going to give us a hint that we should be using Green's theorem in order to maximize our time and our efficiency on this problem here. I guess without further ado, let's go ahead and do the Green's theorem. Well, we have this kind of line integral over c of x minus y dx plus x dy. So let's just go ahead and do this. Well, this is going to actually equal over some region R. We're going to be taking the curl of our f and integrating it with respect to area. So let's just kind of go down the line here. I like to compute the curl first. If you're lucky, and maybe if you're lazy, if you compute the curl of a vector field and it turns out to be 0, then by extension that integral is going to be 0. Obviously we know that is not the case because we already did our line integral, but sometimes it'll be nice because they'll give you a Green's theorem wherein the curl actually evaluates to 0, therefore the integral evaluates to 0, so you can actually save yourself some time there. But anyway, let's go ahead and compute our curl. We know what our vector field is. F is equal to x minus y x. So then the curl of f is equal to the gradient crossed with our vector field. And there is a formula here, especially when we're doing it in 2 dimensions. It would technically be the partial of our y component with respect to x subtracted by our partial of our x component with respect to y, but I find it very helpful actually to just go ahead and make our determinant. You can memorize that, or you can just kind of go through the steps here. So it looks like we're going to have our curl is equal to the partial of x with respect to x minus the partial of x minus y with respect to y. Pretty simple partials here. That's just going to be 1 minus -1, which is going to equal 2. Unfortunately, when we know this already, that we were not as lucky. Okay, let's go ahead and kind of figure out what we need to do here now. We have a double integral, and we know that our region here is a circle. That should be a pretty dead giveaway that we're going to want to use polar coordinates here. So let's just go ahead and convert whatever this is in polar coordinates, because regularly we might have to do what that would be y negative the square root of negative square root of 1 minus x squared is less than or equal to y is less than or equal to the square root of 1 minus x squared. That would be our first bound on our integral, and then the second one would be from -1 to 1. But as we can see, well, our radius is constant all the way through, so that's just going to be from 0 to 1. And then, well, it's a circle. It's not a half circle, it's not a semicircle, it's a full circle, so it's going to go from 0 to 2 pi. We should be familiar with polar coordinates and double integrals by now, so I'm not really going to show too much work on that. Meaning our completed integral here that we will be evaluating is the integral of 2, can't forget our differential, the Jacobian, I guess, 2r dr d theta, And recall that once again, our bounds on r, well, our radius stays constant the entire time. It's just going to be 1. We decided that in the very beginning. And then once again, it is full circle. Therefore, the bounds on theta will go from 0 to 2 pi. And just kind of evaluating this really fast, we're going to actually have, I'm going to skip that first step a little bit. So it's pretty simple integral to solve. The integral of 2r dr is going to be r squared. And evaluating that from 0 to 1 is just going to be 1. So it looks like we just have the integral of d theta from 0 to 2 pi, meaning that's just going to be theta evaluated from 0 to 2 pi, meaning that our Green's theorem proof here says that it is 2 pi. And as you can see, well, let me actually color code this, oops. Keep with the theme. As you can see, using Green's theorem and line integrals, we see that we actually got the exact same answer for both. So that was kind of our motivating example there. A couple of notes here. I guess just kind of note that the line integral side was actually a lot more work. And although I took more time on the Green's theorem, perhaps, just kind of explaining how it works, this was a pretty simple Green's theorem problem, and if we were already familiar with Green's theorem, I bet you we could see how evaluating that pretty simple double integral and computing the curl for the integrand and obviously switching to polar coordinates would be a lot easier than going through our 4 steps: parameterize, change the integrand, solve for the differential, take the dot product, and then finally solve the integral. Just as you can see, just based off my work, the Green's theorem took around half the lines that the line integral side did. Now, with that being said, they're both sufficient. They both get the same job done, but it's going to be a matter of which one is easiest, and that's kind of what Green's theorem is all about. I guess 2 more final notes that I just kind of want to reiterate with this motivating example here is I've said it twice already, and I'm going to make it 3 times now. We really need to make sure that our orientation is positive. That is going to be counterclockwise. That is just kind of, that's the convention that we use in calculus, I guess, is counterclockwise is positive. So that's the first note that I kind of want to make here. And then the second note here is that this notation, when we're given this, so we're going to have this kind of closed integral with that little circle sign of our x minus y dx plus x dy, which is pretty much just the form that I introduced when we were talking about Green's theorem up here, when we have the integral of p dx plus q dy. Whenever I see that, unless it's a red herring and they're trying to get you to do more work on an exam or a homework or whatever you're doing, that is definitely going to be an indicator that we're going to be using Green's theorem. So that was our motivating example. I guess we might as well just go ahead and get into another example. For our next example here, we're asked to evaluate this line integral where the integrand is x squared y dx minus xy squared dy, where c is x squared plus y squared is equal to 4, oriented counterclockwise using Green's theorem. So kindly enough, it would appear that they already told us that it was oriented clockwise. I guess I already told us it was already oriented counterclockwise, so it's positively oriented. That's one of the big things that I have been reiterating. So we really don't need to check that, and we can kind of visualize what this parameterized path kind of looks like. It's just going to be a circle with a radius of 2. And we're asked to use Green's theorem, so we already know that we can just go ahead and convert this integral here over some region C of x squared y dx minus x y squared dy, and that is going to equal a double iterated integral of the curl of f with respect to area over some region R. So just kind of going down the line here, like I said, I like to compute the curl first. So let's just go ahead and compute the curl. For this one, we'll go ahead and actually use the formula for what curl is without, taking a determinant. So it's actually d dxq minus d dyp. And those are both partials. All right, so starting off here, we know that this is our p value and this is our q value. So we're going to be taking the partial of, this is our p, this is our q. So taking the partial of our q, this is going to be the partial of negative xy squared with respect to x, minus the partial with respect to y of our p, x squared y. Let's go ahead and take the partial here. Well, that negative xy squared with respect to x, that x just goes to 1, so looks like the final answer there is just going to be negative y squared. Minus this x squared y with respect to y. Once again, that y is just going to go ahead and go to 1. So it looks like we're going to have negative y squared minus x squared, which can actually be rewritten as, if we just pull out that negative sign, then it looks like we're going to have negative y squared plus x squared. And then, as you can see, if we distribute that negative sign all the way through, these are actually equivalent expressions. So I guess I might have kind of skipped a step there. Not really skipped a step, but I did something in my head. It's a circle, so we know we're going to be using polar coordinates here for our final integral. Our double integral, we're going to be using polar coordinates. So let's just go ahead and set up our integral. We have the double integral. We'll write our bounds in just a little bit of our curl, which is negative y squared plus x squared. I'm just going to go ahead and perhaps skip the writing out of, what it would be in Cartesian coordinates, and I'm just going to go ahead and skip to the fact that, well, we're in polar, so this is at y squared plus x squared is going to turn into r squared. And once again, that's going to be negative, so our integrand is going to be negative r squared. And then we're going to have r dr d theta. Cannot forget our differential r, our Jacobian. Dr d theta, and dr is going to be our inner bound, so our inner integral's bounds are going to be the radius. X squared plus y squared is equal to 4, which is just the same thing as r squared is equal to 4. Take the square root of both sides, r is equal to 2. So our radius is going to go from 0 to 2, and our theta, well, it's a full circle, therefore we're going to be going from 0 to 2 pi. Looks good. We can just go ahead and solve this now. Rewriting and simplifying a little bit. Not really too much to simplify, but we're going to have negative r cubed dr d theta. Let's go ahead and solve this real fast. We're going to have our outer integral be 0 to 2 pi. Well, the integral of negative r cubed dr is going to be negative 1/4 r to the 4th. And then that r is going to be evaluated from 0 to 2. I can't forget our d theta on the outside. 2 to the 4th is going to be 2 times 2 times 2 times 2. So that's 4 times 2 times 2. 4 times 2 is 8. 8 times 2 is 16. So we are going to have negative 16 over 4, which is negative 4. From 0 to 2 pi of negative 4 d theta. And just kind of note that I skipped the step of where we're plugging in 0 because, well, it's obviously going to be 0. Negative 1/4 times 0 to the 4th, no matter how many to the powers we have, and no matter what order it is, it's going to be 0. So our final integral here is going to equal negative 4 d theta, evaluated from 0 to 2 pi. So we're going to have negative 4 theta from 0 to 2 pi. Plug in our 2 pi. We'll show our 0 this time. we're going to have negative 4 times 2 pi minus negative 4 times 0. That is going to equal negative 8 pi minus 0 plus 0, I guess. Those negatives cancel, and it doesn't really matter. Negative 8 pi is going to be our final answer here. And as you can see, that is how we solved this kind of scary looking line integral, perhaps, using Green's theorem, and it kind of simplified it a lot. And like I said, I just kind of used the familiar, not the familiar, the perhaps not so familiar way of computing curl. In my opinion, I would definitely, unless you're extremely confident with, recognizing the P and the Q, and, I just wouldn't risk it. Personally, I would definitely draw the determinant out and make sure that you understand what you're doing. Any more notes here? I guess notes that I've made prior in the very past when we were doing polar coordinates. Just don't forget this r, dr, d theta. That r right there. If you forget that, then your answer is just going to be completely wrong. Another note, I guess, oriented counterclockwise. I made that point in the beginning. It's going to need to be oriented counterclockwise. But overall, I think we kind of have an idea that Green's theorem is going to be a pretty good and nice way of computing maybe more difficult line integrals, or perhaps not more difficult, but more time-consuming line integrals. So I think we have one more example, so let's go ahead and get to that. For our harder example, and note that I just kind of did harder as in, it's subjective for sure, but what I mean by harder is, let's just go ahead and read the problem first. Find the work done by vector field xy, negative y, on a particle moving along y is equal to 3x squared from the origin to 212, then back along a line segment. So the reason that I say this is a little bit more difficult, or perhaps something that we're not used to quite yet, is because, in the past we were doing pretty uniform shapes. So literally the last two examples that we did were just with circles, right? So we actually have some kind of function here. It's a parabolic function, and then we're going to have a line segment, and that is actually just going to form a kind of shape. It's going to be a different shape than what we're used to. It's going to be closed, of course, but it's going to be a shape. And lucky enough for everybody here, I guess, maybe unlucky as well, though, that this is going to be the first live graphing that I've had, probably since quadric surfaces. We'll go ahead and do green. Okay, so first off, our particle is moving along y is equal to 3x squared from the origin to 212, then back along the line segment. So pretty much what this is saying is that, we're going to be drawing a function starting at the origin and going to 212, and the path is going to be y is equal to 3x squared. And then once we get to that 212, we're going to go right back to the origin with a line segment. So let's just go ahead and do that. Excuse my probably botched kind of scale here, but we're just going to go ahead and define this as 212. Y is equal to 3x squared. I'm just going to go ahead and kind of make half of a parabola here. There we go. That is y is equal to 3x squared. All right, well, looks like that first part is done, and then it's going back to the origin via a line segment. There we go. So that's kind of what our shape looks like here. What was this right here? This kind of line segment, what is that slope? Well, it's positive. It's a positive slope. Looks like the rise is 2. And not the rise is 2. The run is 2, and then the rise is 12. Looks like we're going to have y is equal to 6x here. Perhaps it's not too hard for us to convince ourselves that is true. If we plug in y is equal to 6 times 2, that's going to be 12. So that checks out, and then 0, 0 is also going to check out. Okay, well, we have our kind of graph here, and it's actually kind of discreetly gives us one of our checks that we have to make, which is the orientation from the origin to 212, meaning, well, we're starting here and ending here, so we're pretty much going to be moving this way. And then, well, we're moving from 212 back along a line segment. So we're going from here back to our origin. Looks good. Well, perhaps it may be difficult to see now that, this isn't really a circle, but it's, once again, not so hard to convince ourselves that this is positively oriented. This is going to be a clockwise orientation here. So yeah, that should be that, really. Let's just go ahead and ask to find the work. So we know our work is going to be solved via a vector line integral. This is closed, therefore I added that little circle along some path C of our vector field RF dotted with our dr. And I just kind of want to make a note of something really quickly here. Well, if we were to do a line integral here, well, we would actually have to have two different line integrals, right? Why that is because, well, we have one function here representing our y is equal to 3x squared. Well, that's one line. And then we're going to have another path, y is equal to 3x. So pretty much what I'm trying to say here is that we would actually have to do two line integrals, therefore two PIDs. So we'll have two different parameterizations with thus two different integrands, thus with two different differentials, thus with two different integrals. So I guess this is kind of an example here. Why I define this as harder is because, well, technically we are able to do a line integral, but not so subjective now. That will be a lot more work. So let's just go ahead and use Green's theorem. We know that Green's theorem applies. It's counterclockwise oriented. We're finding the work. There's really nothing here that indicates that we can't use Green's theorem here. It's a closed surface, so we should be good to go ahead and use Green's theorem, which states that this kind of line integral is equal to the double integral over some region R of our curl of our vector field with respect to area. Alrighty, so let's just go ahead and do this. Let me see. Let's go ahead and calculate our curl first. Maybe I can take a shortcut. Curl of f, which is going to equal the gradient across our vector field. We are given our vector field. It's not split up this time. We don't have to find it. X, y, and negative y. Top, we're going to have our gradient, d dx. Oops. Partial respect to y. Make our little determinant, which is going to equal the partial of negative y with respect to x minus the partial of xy with respect to y. Well, that negative y with respect to x, that's going to be treated as a constant. Therefore, that's going to be 0. So this is going to be negative, well, the derivative of xy with respect to y. That's just going to be that y is going to turn into 1. Therefore, it's just going to be negative x. So it looks like that's our differential here, or not a differential, our integrand. So for the differential, well, we have two options here. We can either integrate in dy first, or we can integrate in dx first. Just kind of thinking about it here. Well, if we integrated in dx first, we would be going from 6x to 3x squared. And then our y bound would go from 0 to 12. Definitely not too difficult, but the only reason I'm a little bit reluctant on that is because that 0 to 12 may cause for some unwanted powers. Maybe it's going to be a little bit difficult for us to solve 12 cubed or something like that. So we're going to get pretty big numbers there. But kind of looking at our dy here, well, let's just go ahead and use our original technique. We're going to start from the bottom function and exit through the top. And then our bounds on x are just going to be from, well, the origin, 0, to some value, which is 2. So in my opinion, that looks a lot easier than, well, the latter would be, you know, entering from 6x and exiting out of 3x squared, and that's not too bad. But, you know, then our y bound would go from, you know, 0 to 12. So I am actually just going to opt for that orange right there. So let's just go ahead and make our integral, our double iterated integral. Don't worry, I'll color code it in a little bit. Well, our curl is going to be negative x. And then our differential, well, that's, we just said, we're going to go ahead and do dy dx. So for our orange, it looks like our bounds on y, well, we're entering in from y is equal to 3x squared and exiting from y is equal to 6x. So that's going to be our inner bounds, 3x squared and 6x. And then our x value, well, that goes from 0 to 2. Looks good there. Let's just go ahead and solve this. Well, we're going to have that outer integral still be from 0 to 2. We'll get to that later. Negative x differentiated with, or integrated with respect to y, that's going to be negative xy. And then let's just go ahead and that y is actually going to equal 3x squared and 6x dx. So the integral is now going to go from 0 to 2 of negative x times 6x minus negative x times 3x squared dx. Just kind of simplifying here, we have the integral from 0 to 2 of negative 6x squared, and then these two negatives turn into a positive there. So we're going to have 3x cubed dx. And then this should be a pretty simple integral here. Well, we're going to have negative 6 for this first term. We're going to have negative 6 over 3x cubed, which is equal to negative 2x cubed. And then here, we're going to have 3/4 x to the 4th. That's not going to simplify any further. So this is going to be negative 2x cubed plus that 3/4 x to the 4th, evaluated from x is equal to 0 and x equal to 2. Doing a little bit of head math here. Well, first of all, this right side is going to be 0, no matter how we put it. So this first part, well, this is going to be negative 2 times 2 cubed. That's going to be 8. And then plus 3/4 times that 2 to the 4th, we already kind of figured out earlier, but I do it again. 2 times 2 times 2 times 2, which is 4 times 2 times 2, which is 8 times 2, which is 16. And then I guess our final answer here is going to be 2 times 8, negative 16, negative 2 times 8, plus 3/4 times 16. Well, let's just go ahead and kind of divide that to 16 up into 4 times 4. Therefore, one of those is going to cancel, so then this should just be 12. Therefore, looks like our final answer here is going to be negative 16 plus 12, which is pretty simply negative 4. So there we go. That is using Green's theorem on our harder example, so to speak. Is it so difficult? No, not really, but I guess it's kind of good for us to get used to seeing non-uniform shapes. So, you know, shapes like a parabola and then a line segment back to the origin, wherein it makes a closed kind of shape there. I guess there's no notes here other than, you know, it would have been the exact same had I taken it in dx dy. Perhaps more work, perhaps less work. I just chose whichever order I found, you know, in my head to be perhaps easiest, and I'm willing to bet that I chose the right option there because, you know, we probably would have had some kind of x cubed, x to the 4th perhaps in there within our 12. So we would have probably had to pull out a calculator and do 12 times 12 times 12 times 12 and, you know, so on and so forth. So I guess bring back your double integral skills if you've kind of forgotten about them. That's definitely going to come in useful whenever we're doing Green's theorem. Counterclockwise oriented, therefore it's positive, close shape, so we know that Green's theorem applies. And I think that should be it. Thank you very much for watching.